Hi, I'm Jackson Montgomery, accompanied by Sean Bowling, and we're going to talk to you about our self-riding robot. We were thinking, what problems could a robot face? What would happen if a robot fell over? And what would it do? Our first question was, has the robot fallen over at all? And how would it know? If it did, how did it fall? Which way did it go? Then the robot would need to get back upright, so it can go on about its way. So it uses its servo arm to push itself back upright. Then it will wait just a moment to make sure it's going to stay upright, and then continue on.
Next, we want to discuss the methodology our robot follows. First, we decide on our methods for orientation awareness, which included the use of a 3-axis gyro, which will be explained in greater detail later. We also had to determine ways in which our robot would fail to detect a flip. To help with this problem, it was decided to include a mercury tilt switch to help detect a flip. With the use of servos, the robot is then able to flip itself into its proper orientation. Now we will be talking about upcoming technologies related to our project. First, we have the nanorovers. These are advanced robots for space exploration. These miniature robots are capable of self-riding, which in turn helps to adapt and evolve to unknown terrain. And at such a small size, a large amount of robots are able to fit within the projected mass and volume of future space ventures. Next, we have the Alpha Dog. The goal of the Alpha Dog is to provide a payload of 400 pounds over a large distance and over extremely rough terrain, with the ability to right itself if it were to fall over.
For our design, we used an L3G 4200D 3-axis gyroscope, which was really the heart of our design and made the whole thing work. It kept track of changes in the robot's rotational orientation and told us whether or not it had tilted, and which way it had gone. To check to avoid false positives, we used a mercury tilt switch, which was kind of a backup as well. For the brain of the operation, we used our Arduino Uno, and it kept track of all our values and calculations. On top of Arduino, we attached a proto board, which is a platform that can be easily attached to the Arduino, which we added the module for the gyroscope, and the tilt switch, and a few other things. One of the features we added to the proto board was an RGB LED, which indicates which way the robot had flipped over, and also lets us know that it's ready to go. For the arms of the robot, we used 2 small servos with some craft sticks attached to them in order to be able to flip the robot back upright. Also, we used various miscellaneous parts including resistors and wires and other connectors. For the construction of our robot, we started with a foam core board base, which we attached the Arduino and the 2 servos to using command strips. We secured those servos even more using some masking tape so they wouldn't shift around. On top of that masking tape, we hot glued down our battery so it wouldn't move around. For the servo arms, we used some craft sticks hot glued to the arms on the servo. We then added a second battery pack to the bottom of the robot to supply extra power for the servos. For the programming aspect of our robot, we used C, C++ in the Arduino compiler. We also used the servo and I2C header files to provide easier use of these aspects of our program. We used the I2C to talk to the gyroscope module and get the needed values from it. Our overall code is fairly simple and straightforward, although we did use separate functions for our gyro readings and also a separate one for the writing sequence.
Now we'll be talking about various uses for a self-riding robot. As discussed earlier, this technique helps a robot to explore and traverse unknown rugged terrain. Another use is adding a self-riding system to a cleaner bot. This type of technology helps relieve the stresses of keeping a clean house. Sometimes the bot may find that laundry you threw on the ground and tip over. Your house isn't getting cleaner while your robot's on its back. Transportation is another aspect that can benefit from a self-riding robot. This is particularly useful in getting supplies and goods to the people in underdeveloped countries.
Some possible improvements we could make are things such as adding an accelerometer in conjunction with our gyroscope to give us a much more accurate picture of our orientation. We could also use servo motors with better placement and a better arm design in order to have more control over our flip. We'd use higher quality sensors and components to give us overall better quality and accuracy. We could refine our program to better translate the data from the sensors. We could also use a much more efficient power management scheme, so we only need to use one of the 9-volt batteries.
The results we attained from this project proved to be satisfactory. These results included the robot being capable of flipping itself over in a timely and responsive manner. One issue the robot had was that if the flip was slow enough, it had trouble determining which direction it fell. To overcome this, we added a failsafe that activates the second servo if the first failed to flip the robot. In conclusion, it is critical for a mobile robot to be able to right itself into its proper position, independently from human interaction. An immobile robot is an ineffective robot.